What if I told you that the most powerful AI models, the ones generating stunning images and understanding complex language, learn their incredible abilities through a process that's secretly quite simple, yet mathematically elegant? It's a method so fundamental, it's the backbone of nearly all modern AI. We're talking about backpropagation, the engine that drives neural network learning. It's how these digital brains adjust themselves, correcting their mistakes over and over, until they become incredibly accurate at tasks like recognizing faces or translating languages. Imagine a neural network as a team of chefs trying to perfect a new recipe. Initially, they just guess the ingredient amounts. They mix everything, taste the dish, and it's probably terrible. How do they figure out who added too much salt or not enough spice to make it better next time? This is exactly the challenge a neural network faces. It makes a prediction, compares it to the correct answer, and finds out it's wrong. But how does it know which of its millions of internal connections, called weights, or its biases, the thresholds for activating a neuron, are responsible for the error? Before backpropagation, training neural networks was like trying to tune a complex orchestra by randomly twisting knobs and hoping for the best. It was inefficient, often impossible for deep networks. This is why for decades, AI research struggled. The breakthrough came with backpropagation, which provides a systematic way to distribute blame for errors. Think of it as a two-step dance, first, the forward pass, then the backward pass. In the forward pass, data enters the network, travels through each layer, and eventually produces an output, the network's prediction. Like our chefs making their initial dish. Next, we calculate the loss or error. This is simply how far off the network's prediction was from the actual correct answer. If the network predicted cat but the image was a dog, that's a big error. Now for the magic, the backward pass, or backpropagation itself. This is where the error signal travels backwards through the network, from the output layer all the way to the input layer. Each connection, each weight, and each neuron's bias gets a specific blame assignment. It's like the head chef tasting the bad dish and telling the sous chef, "Too much pepper." The sous chef then tells the line cook, "You added too much pepper to your sauce." Mathematically, this blame assignment uses something called the chain rule from calculus. Don't worry about the complex math, the intuition is what matters. It allows us to figure out exactly how much each tiny adjustment to a weight or bias would reduce the overall error. So, if a weight contributed a lot to a large error, backpropagation tells us to adjust it significantly. If it barely contributed, it gets a smaller adjustment. This is called calculating the gradient of the loss with respect to each weight and bias. Once we have these gradients, we update the weights and biases. We nudge them in the direction that reduces the error. This is often done using an optimizer like Atom or SGD, which are just smart ways to decide how much to nudge. This entire process, forward pass, error calculation, backward pass, and parameter update, is one training step. Neural networks repeat these steps thousands, even millions of times, with different batches of data. With each iteration, the network's internal connections get refined. The weights and biases slowly converge to values that allow the network to make highly accurate predictions. It's how a raw, untrained AI actually becomes intelligent. Backpropagation is the reason deep learning exploded. It allowed us to train networks with many layers, unlocking their potential to learn incredibly complex patterns that nobody could program by hand. So, the next time you marvel at an AI's ability to generate text or recognize objects, remember the elegant dance of backpropagation happening secretly beneath the surface, constantly refining, constantly learning. The key takeaway is this: backpropagation is the mathematical engine that allows neural networks to learn from their mistakes by efficiently distributing error information.